Hello everybody, I'm Theodore again. Today just want to discuss a little more about a very uh, controversial topic, one that is called nuclear waste. People opposing nuclear power have often quoted or have been quoted saying, waste is the big problem. We can't get rid of it, it's here for millions of years and we don't know what to do with it. And we are spending billions of dollars every year because we need to put it away somewhere, making sure no one gets their hands on it to do something nasty with it. And for that kind of reason, it's probably one of the main arguments against the use of nuclear power. So people will ask, what do you want to do with all this nuclear waste? Now this video is going to discuss one of the possible options that we can make nuclear waste perhaps useful again. So if you think about nuclear waste, you'll probably think of these, barrels with those radioactive labels on it. These very menacing looking things. And that adds to all the fear factor. But let's just first do something by demystifying what nuclear waste is. So let's take a look. I'm going to Google cask storage nuclear waste. So this is what real nuclear waste looks like. It's not nearly as menacing looking. And inside each so-called cask of nuclear waste, there is something we call spent fuel rods. What are spent fuel rods? Now you see when uranium is taken out from the mine, it gets processed into nuclear fuel. That itself is not that radioactive. But when it undergoes fission, where the atom splits in two, so you can Google nuclear fission. So you see nuclear fission, the atom splits in two, and then you see these things here called fission products. Now these fission products, they are very radioactive, and they'll emit alphas, betas, gammas, stuff that can cause cancer. Okay. So you may have heard of some of these fission products before. These are known as cesium-137, iodine-131, strontium-90. These are just some of the fission products that people are very scared of, and they'll try and trace when they leak into the ocean. For example, we have this Fukushima Fukushima accident, where cesium was being traced in the waters, the Pacific Ocean, if I'm not wrong. So you can see cesium-137 Fukushima. Yep, and you see all these pictures of the cesium actually spreading around the ocean. And it looks very scary and all. You see this plume over here? See this plume over here, just in the center of what I'm highlighting? Yeah, this all looks pretty scary. Now, what is so scary about radiation is that it can cause cancer. And how does something like cesium, for example, cause cancer? Well, let's say you have let's say you have a cesium atom, cesium-137. Now, what happens with this atom? This atom is very energetic, and it undergoes something called beta decay. So I'm going to draw an arrow. I'm going to write here beta decay. Yep. So this beta decay will convert this cesium-137 into barium-137. So what happens after that? Usually what happens is that a gamma ray actually comes out, and that will turn it into a stable form of barium. Okay. So let's write stable here. Now this gamma ray is going to shoot off. Okay, it's going to shoot off, and it will probably hit some part of your body, So you're just going to look for a picture of DNA. So you don't want it to hit your DNA. So if you look at Wikipedia, what the DNA picture looks like, molecularly it looks like these 4 basic base pairs inside your DNA. Oh, okay, that doesn't look too good. Let me use that snipping tool. Oh. There you go. Now this gamma ray is going to hit your DNA. What's it going to do? It's going to damage it. And what your body usually does is that you have natural enzymes, natural proteins that will actually kind of try and fix your DNA up a bit. So the gamma ray actually hits this carbon skeleton. So you see this phosphate group here, carbon, oxygen. So the gamma ray will hit one of these atoms out of place, and there you have DNA damage. So normally your body has natural defense mechanisms to repair this DNA. So yeah, well, you have a straight line is now broken into 2 bits. So let's say this part will break off. So what your body naturally does is that you will have some special proteins or special enzymes to kind of repair this DNA. And that works up to a certain threshold. If there's too much of these gamma rays, your defense mechanism, your self-repair mechanism is overwhelmed, and the cell actually ends up dying or mutating, thus giving you the dreaded cancer everyone's fearing. Now, so we know radiation is pretty good at damaging stuff. Take for example the DNA that we don't want being damaged. Yep, take for example the DNA we don't want to get damaged, right? Because there's a long carbon skeleton with phosphate groups there, then we don't want it to be damaged. Now, so how can we make use of this damaging property? Well, let's take a look at the molecular structure of plastic. Okay. Alright, again we go to Wikipedia. You can find various kinds of plastics over here. Okay, this is not Wikipedia, but yeah, okay. This is a very typical plastic structure. They call it polyethylene. So it's from sciencehistory.org. And let's see. Yep, plastic will look something like this. So I'm just gonna... Okay, this is not plastic.
Are you looking too?
Yeah, plastic will look something like this.
I know, but you never said if you were.
Okay. So this is plastic. Alright. Now plastic normally cannot be biodegraded, and normally it needs something like UV rays to damage it in order for it to be biodegraded. So let's take a look at one more molecular structure of something that is biodegradable. For example, fatty acids. So we go and look. Yeah, if we take a look at If you take a look at the
Send it off with good luck to wherever it's going. Sorry for
no, it's okay.
Is it at the laptop hospital?
If you take a look at some of the fatty acids that are actually biodegradable, we take a look. This part, which I'm circling here, that looks exactly like a typical plastic molecule. So these are the carbons, and the hydrogens are not drawn there. But what is different is that at the end of it, there are a few oxygens added to the carbon. Okay? So, when we look at this molecule of plastic here, when the gamma ray actually hits this plastic molecule, it's going to break this bond here. And I'm just going to draw. Okay, it's being cut in half, so to speak, like a scissors. So this gamma ray is like a scissors for the plastic. And what happens to these ends? This ends here, and this ends here. It's become what is known as free radicals, and they are very reactive. And they'll probably react with anything that's around them. In fact, if you have something like oxygen, if you have oxygen around them, okay, if you have a, let's say, a nearby oxygen molecule, that's nearby when these things happen. What happens is that this oxygen will attach itself to the carbon. Okay, the oxygen attaches itself to the carbon. Maybe this one will attach itself here. Now the mechanism isn't exactly like that. There's a lot more detail that goes on. But in fact, if you irradiate plastics with UV or X-rays or gamma rays in the presence of oxygen, this is what will happen. And this process, people call it photo-scission. You can take a look at some of the sources I'm putting in the description below. So what happens is that when you add oxygen to the plastic, it starts looking a little more like fatty acids. And fatty acids are what bacteria and fungi like to eat for lunch. So, where have we seen this before? Is this in scientific literature? The answer is yes, of course. If we take a look at this link I have here, it says that, okay, it says that in this title, it's called Biodegradation of Gamma Irradiated Low Density Polyethylene and Polypropylene. These are very common plastics by endophytic fungi. This just means, endophytic just means that it exists inside a plant. Okay, so what are the highlights and the abstract? So the exposure to gamma and radiation results in the weakening of the bonds, which facilitates the endophytic fungi to colonize the polymer. So what it means is that, hey, before irradiation, the fungi cannot eat the plastic. But after irradiation, when you cut up the plastic using gamma rays, so to speak, the plastic actually becomes more biodegradable. And you know, plastic is a very global problem. People worry about it a lot. That's why there's been a big shift moving towards recycling, using of paper bags, metallic straws, etc., etc. So this is yet another waste problem generated by us. But we can see that the potential for nuclear waste, which emits lots of gamma radiation, the potential for using nuclear waste as it is to, let's say, degrade our plastic waste and make it biodegradable is there indeed, because it's been scientifically proven in literature that gamma rays can cause plastic to become biodegradable. So This effectively makes it possible to use one waste problem to solve another waste problem, since we have lots of plastic lying around anyways. And since nuclear waste will be there for quite a long time, and it's going to be there emitting gamma rays which can potentially be useful for degrading plastics, it may not be such a problem after all to have some of these nuclear wastes lying around, because they are potentially useful. So in summary, this video is just exploring one possible use of nuclear waste, which is a nuisance to us, which is a potential nuisance to us, and use it or recycle it to do something useful for us. For example, break down plastics, which is also another nuisance for us to handle. So thanks for watching. I'll see you guys next time when we have other interesting ideas to discuss. Bye bye.